So good evening, everyone, and welcome to the fourth session of IEEE CodeX Sri Lanka session series. IEEE CodeX Sri Lanka is a national initiative under the IEEE Sri Lanka section. Our goal is to build a strong and supportive community of students passionate about competitive programming and problem solving. It's great to see all of you here with us once again. Whether you've been with us since the beginning or have joined along the way, you're now part of a growing community. You're part of CodeX. I'm Sajid, your moderator for today's session, representing CodeX Sri Lanka team. I'm excited to guide you through another valuable session in your journey towards becoming a better coder. Now, before we dive in, let's quickly revisit what we did in the last session. On the 17th of July 2025, we hosted our third official session, which brought together over 100 undergraduates from across Sri Lanka. The session was led by Mr. Lakshit Nishanki, where we explore the world of problem solving through sorting algorithms and binary search, strategies to apply them in contests, practical techniques for solving problems efficiently. It was an engaging and interactive session that helped the participants strengthen their foundation and gain valuable insights for competitive programming. Today, we are taking the foundation one step further. For today's session, now on today's topic, tonight's session will cover one of the most powerful techniques in problem solving, dynamic programming. Mastering these concepts will give you a serious edge in both contests and interviews. Before we move into today's session, we'd like to make a quick announcement. As you all know, certificates of participation will be awarded at the end of today's CodeX session series based on your attendance and engagement throughout the program. To facilitate, we kindly request all participants to rename themselves using the name you used during registration. That helps us accurately track your participation and evaluations across sessions. I'll repeat this once again. To facilitate this, we kindly request all participants to rename yourselves using the name you used during registration. Now, let's get into it. It is with great excitement that we welcome a truly outstanding team to kick off our fourth Codex session, Team Insomniacs. Team Insomniacs is a powerful competitive programming team with a country rank first at both IEEE 17.2 and 18.2 and a global rank of 65 in IEEE 17.2 and a global rank of 66 in IEEE 18.2. Renowned for their consistent performance in global competitions and deep expertise, we are privileged to have them share their insights with us today. So without further ado, please join me in warmly welcoming Team Insomniacs to Codex Sri Lanka. Over to you.
Okay, thank you, Sajid. So, can someone confirm that they can hear me? Because my connection is not good today, so I have decided that I will not switch on my microphone. Am I audible? Hello? Hello?
You're audible.
Okay, thank you. So, I'm not having a good connection today. So, I will first apologize for that. And okay, I think you should allow me to share my screen. Okay, thank you. So, okay, now I hope that you can see my screen. Can someone confirm that as well? We have to go all of these things
Yes,
because I'm not having a good connection. Yeah, okay, thank you.
we can see your screen.
Okay, thank you. So, if I'm not audible at any point during my presentation, please let me know. It means that I have got my connection disconnected. Okay, so first of all, I would like to introduce ourselves. So, we are Team Insomniacs. I have my colleague Praveen Sumanasekara with me today. I'm Athulya Ratnayake. Unfortunately, Buddhi will not be able to join with us today. but don't worry, we will take you through this topic. So today we are going to talk about dynamic programming. So first of all, let's see what is dynamic programming. Dynamic programming is an optimization technique. What is an optimization technique? Now, I'm pretty sure that you have participated in some of the competitive programming competitions before. So when you have encountered, when you try to solve some problems in dynamic programming, not in dynamic programming, under any topic, when you are submitting your solution, you might have got this message. Time limit exceeded. Have you come across this message? Please raise your hands if you have that. If you have. If you have seen this message earlier, please raise your hands because I need an engaging audience. That is how I can make sure that all of us are in the same page. Okay. Praveen, yeah, thank you. I know that, okay. We got that message together when you were there. Okay. Only two? Come on. Okay. 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 It means that you are aware about this message. So this message means that you have not optimized your code efficiently. It means that you should do better. So what is optimization? So there is something called the time complexity. This big O guy. Big O. So when you write a code, there is a time complexity associated with that. You are getting this message because your time complexity is higher than the expected time complexity. Let's say the problem setter expect you to solve it with ON, or the linear time complexity, or an algorithm with linear time complexity, but your solution is ON square. If you are not aware about this time complexity, it's okay for now, but you should learn this if you are willing to do computer programming in the future. This is a must. So if the problem setter needs you to solve the problem in linear time, if you are going quadratic, it means that you are not doing well. So then you will get this message. So when you get this message, in certain cases, you can use dynamic programming to take this to this, not always from this to this, but to reduce time complexity, you can use dynamic programming. So you're going to do that by breaking your problem down into several subproblems. We will see how we can do that, but for now, you need to have this in your mind. What you're going to do is you're breaking your problem into smaller subproblems. And that is how you are going to optimize the problem. Now, when I say this, you might think that, okay, this is just an optimization technique. So there is no significance of learning this. But from my experience, I started computer programming back in 2022. So I've been doing that for more than 3 years now. So in my experience, there are more than 30% of the problems in all competitive programming competitions which can be optimized using dynamic programming. You can apply this for graph problems, sometimes mathematics problems. It can come in different flavors, but still you can use dynamic programming to optimize. But you need to admit that every problem cannot be optimized using dynamic programming. So what are the problems that we can optimize using dynamic programming, and how can we identify these problems? To have a good understanding about that, we need to talk about the properties of dynamic programming. So I am going to talk about two properties today. One is the optimal substructure. Optimal substructure is nothing but you should be able to divide the problem into subproblems. That is this substructure. So what is optimal substructure? Substructure is being able to divide the problem into subproblems. Optimal substructure is when you have divided your problem into subproblems, the optimal solution for each problem should lead you to the optimal solution of the original problem. When you have a problem, you need to be able to divide that problem into subproblems, and the optimal solutions for those subproblems will lead you to the optimal solution for the given problem. Don't worry if you are not getting any of these things now. We will see this in action in few minutes. So just understand these things. Just try to remember these things for now. When you are dealing with examples within today's session, you will see what I meant here. So I will take up some examples too, and Praveen will only talk about the examples, how to solve problems. So to solve problems, we need to have these concepts within our heads. That is how we can tackle any problem. So to make sure that you all are familiar with the theories, I decided to start with a very theoretical aspect. Then the second property is overlapping substructure. Now we have agreed that to use dynamic programming, we need to have a substructure and it should be optimal. Now I'm saying that, okay, we have a substructure, it should be optimal, and there should be an overlapping nature. What is an overlapping substructure? You can see the figure here. This P is the problem that we have in our hands. And suppose that we can divide this into subproblems. This is subproblem 1 and this is subproblem 2. The part that I have colored in red is the subproblem 1 and the part I have colored in blue is the subproblem 2. Now, you first solve this red color subproblem. It is S1. When you solve S1, then you go to solve S2. Now you can see that when you are solving S2, you already have the solution for S1. So when you are trying to solve S2, without solving this from scratch, you can use the solution you already have in your hand because you have solved that earlier. So you have the solution. So when you are trying to solve this S2 problem, you can use the solution you have obtained from solving this S1 problem. So that is how we are going to optimize our problem. Now suppose if we have something like this, let's say this is S1 and this is S2. S2 is somewhere here. S2 is something like this and S1 is something like this. Now, when you are trying to solve S2, even though you have already solved S1, this does not have an overlap. It means that you cannot use the solution here, the solution you obtained by solving S1 in solving S2. So it means that this will not do any optimization. So if we don't have the overlapping nature, still DP would work, but it will not optimize the code. So I'm not saying that DP would not work. I'm not saying that it will give errors, but it will not solve your problem. Still, you will have the same time complexity. So you should understand that when you are trying to use dynamic programming, you need to check these two properties. Now, it might not be trivial to you when I am saying it like this, but if we actually put this into context, you will understand how it's going to happen. So now we are going to do that. We will take up an example and we will see how this overlapping substructure helps you in optimizing the code. Now this Fibonacci sequence to find in the nth Fibonacci number is the most famous problem in dynamic programming. So the problem is very easy. You are asked to find the nth Fibonacci number. Now please raise your hands if you know the Fibonacci sequence. Now this question is critical. If you know, please raise your hands. Otherwise, I will explain the Fibonacci sequence from the beginning. Okay, I have see how many raised hands we have. How can we? Okay, only 9. Come on. We have 48 participants here. We subtract 7 for the organizing committee. We still have 40. Fibonacci sequence. Okay, please lower your hands. Now raise your hands if you don't know Fibonacci sequence. I think that is effective. Because there are certain people who are lazy to raise their hands. Pathetic, huh? Come on, so it doesn't matter, right? If you don't know Fibonacci sequence, it's not a big deal. I will teach you. Not knowing something is not a bad thing. It is a very good thing. So you can go and learn. Come on. So we don't have anyone who is not familiar with this concept. Okay. So I assume that there are certain people, but they are afraid of raising their hands. Therefore, I will quickly go through what is Fibonacci sequence is. So Fibonacci sequence is a recursive sequence. It is defined like this. F0. F0 is the zeroth term of the Fibonacci sequence, and we define it to be 0. F1, the first term of the Fibonacci sequence, we define it to be 1. Then any other term which is greater than 2, greater than or equal to 2, obviously, because we have already defined 0 and 1, and we are not dealing with the negative numbers here. So it is given by this equation. So suppose we need to find F2. Let's F2. It is given by Fn minus 1, means F2 minus 1, F1, plus F2 minus 2, F0. Now F1 is 1, we know that, plus 0, this is 1. If we need to find F3, we can see that Fn minus 1 is F2, plus Fn minus 2 is F1. Now we know that F2 is 1, and F1 is also 1, so this is going to be 2. If we need to find F4, it is F3 plus F2, 2 plus 1 is 3. So it goes like this. So that is how the Fibonacci sequence goes, and now we need to find the nth Fibonacci number. So for the purpose of explaining, for sake of simplicity, I will take n equals 5. It means that we need to find the fifth Fibonacci number. So when we have this recursive structure, we can draw something called the recursion tree. This is the recursion tree. The idea here is to find F5, you need F4 and F3. To find F5, you need F4 and F3. Why? Because you have Fn minus 1 and Fn minus 2 here. So we call this is the recursion depth. Recursion depth here is 2 because you need 2 previous numbers to find this. So this is the recursion depth is 2. So you need F4 and F3 to find F5. Okay, so now you don't know F4. To find F4, you need F3 and F2. Likewise, you can go this side, and to find F3, you need F2 and F1. And in the bottom level, these leaf nodes, you can see that I have used the red color for those terms. I use that color because we know that. So here we know F1. We know F1 is 1. We know F0 is 0. Likewise, we know all of these leaf nodes. Then we can calculate F2 using F1 and F0. Then when we know F2, we can use F1 to calculate F3. Starting from here, we will use F1 and F0 to calculate F2. Then we can use F2 and F1 to calculate F3. Likewise, you can come from this side and find F4, come from this side and find F3. Then you can add these things together to get F5. Now, when you see, when you look at this problem, you can see that now when, let's say we have found F4, for a moment we will assume that we have found F4. We have come through this path and we have found F4. Now, when we go to this side of this tree, you can see that we need to find F3. But we have found F3 here. We have already found it. When we are finding F4, we have already found the answer for F3. So no point of solving it again to find F3 here, because we have already found it. We have already did all the work to find F3. So we can, if we have this solution here, we can directly use it here. So this entire branch is going to be disappear. So the computations that we need to find all of these guys will not be there anymore. Here also, when you find F3, you have come across F2. So this part will also not be not there. So you can see how we can reduce the number of calculations here. So we are doing that by, now let's say when we are finding F4, we have found F3. So we are storing all the solutions that we have obtained in the process of finding another solution in sum of data structures. Let's say we store it in a dictionary. It's better to use a data structure which has constant lookup time. That is not the scope of today's discussion. Therefore, you can search the data structures that you can use. When you have found F3, when in the process of finding F4, you can store that in a data structure. Then when you encounter this problem from this side, you can see whether you have the solution in the data structure. If you have, you can directly use it. Is this clear? Is this clear? Please raise your hands if this is clear, if you can get what I'm saying. If you see how the number of calculations is being reduced. Okay. I always have the same set of guys who are raising hands. Come on. Okay, thank you. Thank you very much. Okay, so I assume that you all have got it. If you have any questions, you can drop it to the chat box. If you are brave enough, you can unmute your microphone and ask the question. So if you have any question, please do not hesitate to ask, because in competitive programming, it means in competitive programming, we don't have anything called wrong answers or wrong questions, because in competitive programming, if you have done at least one competitive programming competition, you know that how many times we come across wrong solutions. Those are not wrong. Those are not, okay, those are inaccurate, not wrong. So there are no wrong questions or wrong answers. So do not hesitate to ask questions, or do not hesitate to answer when I ask you a question. You can use the chat box. I think, okay, you can direct the message to me, but it's totally all right to drop it to the public chat box so the others can also see the problem. If you are not confident, you can direct it to me, but I will not say your name out loud. Okay, so now you see how we can optimize this using the concept of dynamic programming. So this is the essence of dynamic programming, where you have, when you find a solution to a subproblem, you store it in a certain data structure. Then when you encounter that subproblem again, why are we encountering the same subproblem again? That is because of this overlapping substructure. If you have overlaps, now here, when you try to find the solution for S2, this S1 problem is within this problem. So this part of the problem will, you need to find the solution. So when you are finding the solution for S1, if you have stored the solution in a certain data structure, when you are trying to find the solution for S2, you can take that solution and to save a lot of computational power. So that is how we optimize optimize codes using dynamic programming. Okay, now we have come across all of these topics, and now you might be asking me, okay, what are the types of problems that we are getting in dynamic programming in actual competitive programming competitions? How we can identify a problem, whether it is a dynamic programming problem or whether it is possible to use dynamic programming for this problem, how we can identify that. So there are certain problems. There are two types of most popular problems that we have in competitive programming. One is counting problem, not problems. Sorry. Let's see. Like this, otherwise it will give a different meaning. Counting problem. The first problem is the counting problem, and the second problem is the optimization problem. In counting problem, you are given a scenario, you are given a task. So you need to find the number of possible ways, or all the possible ways to do the task. Either the number of possible ways or all the possible ways. So that is the counting problem. And the next problem is optimization problem. Optimization problem is, out of those all possible ways, what is the most optimal one? Most optimal one in the sense that what is the one with minimum cost. So we'll see what this cost is in a few seconds. So this is the optimization problem. So we will take this scenario to see what the counting problem is and what is the optimization problem is. Okay, now here's the scenario. We have two cities, city A and city B. And we need to go from city A to city B, and we have this good old-fashioned car. This car is capable of traveling 300 kilometers per day. You cannot go more than 300 kilometers per day, but it is totally all right to go less than 300 kilometers per day. It is pretty obvious, right? And there are certain places that you can spend the night. Let's say motels. You have motels in these places. These motels have different rates for one night. In this motel, I'm not sure why used letter F here. I cannot recall that. For a okay, let's forget that. This is a motel. So this motel has a 2,500 Sri Lankan rupees rate. This is 3,500. This 3,250 and so on. So when we are trying to go from city A to city B, counting problem asks us the number of different ways that we can go from city A to city B. So number of different ways means where are we going to spend the times? Now one obvious way is to stay at all the motels. You can stay at the first motel, then travel 50 kilometers in the second day, then stay here, then 200 kilometers in the next day and stay here and so on. And another way that you can do is you can, without spending the night at this F0, you can directly go to F1 because from A to F1, the distance is 250. So you can cover it using this car. So you skip this and you directly come to F1. Then after that, you can skip F2 and come to F3. Then you can, let's say you stay the night at F4 and in the last day you go to city B. So this is another way that you can go from A to B. So there are a number of possible ways to go from city A to city B, but this is not possible, right? Let's say you start from A, then you spend the first night at F2. That is not possible. Why? Because from A to F2, we have 450 kilometers. That is impossible because you can only go 300 kilometers per day using this car. So that is the counting problem. You need to find the number of valid ways, number of legal ways. So when they give you the problem with the wordings, you will see that, okay, I need to count the number of possible ways. If that is the case, 90% of the times it is going to be a dynamic programming problem. And the most popular problem structure in dynamic programming is this optimization problem. In optimization problems, you should not find the number of possible ways, so you should not find all the possible ways, but they ask in the most optimal way. I mean, this context, what is the most optimal way means? It means the way that you can travel from A to B with minimum cost for motel. For an example, let's say that you start from A, and when you see these two, you see that F0 is cheaper when compared to F1. So you decide to stay here, let's say, then you spend 2,500 rupees. Then you do not stay at F1, but staying at F0 will force you to stay at F2. Why? Because you cannot go straight to F3 because from F0 to F3, there is 350 kilometers. So you should stay at F2. So it will cost you 3,250. Then after that, again, you will be forced to stay here. It will cost you 4,000. So then you can go to city B. So this will add up to 9,750. This is a solution. Now suppose instead of staying here, even though this has a larger rate, a bigger rate, you decided to stay at F1. It will cost you 3,500. And after that, you can come to F3 without staying at F2 because the distance between F1 and F3 is 300 kilometers. So you can come here. So you will have to pay 2,000 rupees. Then after that, from F3, you can directly go to city B because the distance is 250. So no more. You should not pay for motels again. So this will give you 5,500. Now you compare these two, you can see that this has the minimal cost. Now for this problem, this is the optimal path. So this is the path with the minimum cost. So this is the optimal path. So we need to find this path. So this is the optimization problem. Now please raise your hands if you have got this concept, the concept of counting problem and the optimization problem. Then we will take an actual example in competitive programming. Easy. It might be an easy example, but it contains all the theories that we should learn in dynamic programming. Or not all the theories, but the most important ones. Okay, now the literature suggests that the dynamic programming can be used when greedy algorithms fail. What are the greedy algorithms? Okay, come on. Now, can you again raise your hands if you know what a greedy algorithm is? Ah, great, great. We have a good audience here. Oh, great. Thank you. So, a greedy algorithm, to talk about greedy algorithms, we need to have the idea about the states or the state space. So, what is a state? State is a snapshot of the problem, a snapshot of a certain instance of a solution. For an example, let's say, okay, we will take this coin example and we will talk about the greedy algorithms. Okay, so the problem is given a set of coins and we are about to pay R rupees using minimum number of coins. Now, when you see this problem, can you drop to the chat box whether this is a counting problem or an optimization problem? We need to find the way of paying R rupees using minimum number of coins. Is this a counting problem or an optimization problem? Okay, I have one answer. I need more. I need at least 5 answers to continue. Until then, I will not continue. I have only one answer. Please don't hesitate to give answers. I will not say your name out loud. I have only one answer. Come on. Can I have another 2 answers? Let's see. Because I'm pretty sure that I will not. Okay, I have another answer. Okay, I have 3 answers now. Okay, you keep on answering. I will continue with the discussion. So this is an optimization problem. Why is that? Because we are not being asked to find all the possible ways or the number of possible ways. And I have forgot to mention, sorry for that. When you have this optimization problem in your hand, you will have this word minimum. Almost always you have this minimum, the minimum, or it will have a word which conveys the idea of the optimal solution. Now here you can see you should use the minimum number of coins. You should not find all possible ways to pay R rupees. They ask you to find a one method which minimizes something, which minimizes the number of coins. And that is exactly what an optimization problem is. In optimization problem, if you have encountered this in mathematics, you know that optimization is nothing but minimizing or maximizing something over a given domain. And we know that minimizing something is equal to maximizing something. We can convert the maximization problem to a minimization problem. That is math stuff. I will not go and dive deeper into those stuff. But finding the minimum solution is the optimization problem. So this problem asks us to find the minimum number of coins. So you need to perform this task. You need to pay R rupees by using minimum number of coins. So this is an optimization problem. So let's take our case 1. We have these set of coins 1, 2, and 5. So you need to admit that we have infinite number of coins, infinite number of 1 rupee coins, infinite number of 2 rupee coins, infinite number of 5 rupee coins. We don't have any other coins. We have only these 3 coins, but we have infinite number of coins. And we need to pay 12 rupees. Okay, now a greedy algorithm. Greedy algorithm that we can see here is, I will tell you the greedy algorithm first, then I will say what is a greedy algorithm, the general definition. Now, a greedy algorithm that we can think about is, we start from 0 and we start paying. We will take the highest numbered coin from this list without exceeding this limit. We take the highest highest valued coin from this list without exceeding this limit, this number. So from 0, we can take the 5 rupee coin. It will take us to 5. We have still not exceeded the 12 rupee threshold. Then after that, again, we can take from these 3 coins, we can take the 5 rupee coin. We will end up in 10. After that, we need to find a coin. So we go to this list and we check. If we take 5 rupee coin, we will go beyond 12. It will make it 15, and that is not legal here. So we cannot take 5. Then we go to the second largest one. So 2. Okay, we can take 2 rupee coin. This will end up, we will end up by at 12. So now we have solved the problem. So this is the answer. And this is the optimal answer. You can see that. We cannot have another answer which has less number of coins. This is the optimal answer. Now the greedy approach is, now let's say this one here. We call this a state. At a given instance, the total that we have paid is a state. Praveen will do an extensive discussion about the state space in the latter part of this discussion, so I will not go into details. But this is a state. This is also a state. From going from 0 to 12, all these intermediate steps are states. So when you are in this state, you are only considering the very next state. You are not considering the consequences of getting a 5 rupee coin at this point. You only considered about the next stage. To find, now you know that the target is 12, but when you are selecting the coin, instead of checking whether we are not going, checking whether we are going beyond 12, we are not actually thinking about the next steps after this state. Now say if we are in this state, when we take 5 rupee coin, we are taking that because that is the largest coin that we can take from this list, and we assume that it will take us to our target rapidly. That is our understanding. That is our idea behind this algorithm. Now this looks okay, right? Because this gave us the correct solution. But there are certain cases where this greedy algorithm fails, and we will take an example and see how this greedy algorithm fails. Here we have a set of coins 1, 3, and 4. In Sri Lanka, we don't have 3 and 4 coins, but to explain how greedy algorithm fails, I had no choice. I had to take these 2 coins. There might be other ways that we can build up this solution using the coins that are already in Sri Lanka, but I don't like to pay that much effort to design a problem. So let's see. Let's assume that we have 3 and 4 rupee coins in Sri Lanka. If you don't like to do that, you assume that this is not Sri Lanka, right? So we need to pay 6 rupees, and we have these 3 coins. Again, we have infinite number of coins, infinite 1 rupee coins, infinite 3 rupee coins, and infinite 4 rupee coins. But we don't have any other valued coins. Now, we will apply our greedy algorithm to this problem. Start from 0, and we check this list. The highest number is 4. Okay, we can take a 4. It will not take us beyond 6. This will take us to 4 rupees. And after that, you go to the list. You cannot use the 3 rupee coin, the 4 rupee coin. It will take you to 8, which is greater than 6. You cannot use 3 rupee coin either. It will take you to 7. So the only option is using the 1 rupee coin. It will take you to 5. Then after that, again, you cannot use 4, you cannot use 3. The only way that you can go is by using 1 rupee coin. So this will give us this solution. But when you look at this problem, you can see that there is a solution like this. 3, 3 is the optimal solution. Because we have infinite number of coins, 3, 3 is the solution. Now, why we ended up with this solution? That is because at this stage, this is called the initial state. Praveen will discuss about the state space. So when we are in this stage, when we are deciding the next state, we did not considered the consequences of coming to this point. When we come to this point, we have no option left other than taking 2 1 rupee coins. So when we were deciding to take 4 rupee coin here, we did not consider the consequences that we are going to face after that. So that is a greedy algorithm. A greedy algorithm does not consider the consequences of the decision taken at a certain state. It only considers the next state. Is it clear? Please raise your hands if this is clear. Okay. So if you have any questions, you can raise in the chat box. Only 2 raised hands. Come on. The others can't you? Okay, I can see some people I know here. Okay, the people I know knows that I know them. So please raise your hand if you have got it. Oh, okay. No, still. Come on. 11 raised hands. Well, okay, this is great. I need 20. Come on. Now I'm thinking bigger. Previously, I wanted only 5 raised hands. Now I have 13 raised hands and 1 thumbs up. Okay, I'll count it as 16. Okay, I need another 4. Come on. 16. Great. 17. Okay. Now don't raise your hands if you have not get the point, right? Okay, I have 20. Come on. Thank you, guys. So I hope that you raised your hands because you got that, not because I insisted you to do so. Okay, so again, I'm remembering you that if you have any questions, you can drop it to the chat box. I will not chase you down. I will not stalk you in social media and see whether who has asked that question. I barely remember names. So that is not going to happen. So if you have any question, you can drop it to the chat box. I'm pretty sure that Praveen is also not good at remembering things. So you can do the same thing in his part as well. So now we have realized that the greedy algorithm does not work here. So what is the path that we can pave to solve this problem? That is by using the concept of dynamic programming. Here you can see that to have a sum of 6 rupee, these are the possible ways that you can come to 6. Now suppose you are in this state. Let's say you are in this state. Now you have a very ground level understanding about states. Certainly there are people who are pretty much aware about this, but from the things that I have taught today, you have a naive idea about what is the state space, what is a state. Now let's say you are in this state. So what are the previous possible states? You have these 3 coins, 1, 3, and 4. So given that you are currently at this position, it means that previously either you have been in this position or this position or this position. How? If you were in this position previously, you can spend 1 rupee coin and come to 6. If you were in this position, you can spend 3 rupee coin and come to 6. From this, you can spend a 4 rupee coin to come to 6. Now you can see that this depends on the set of coins that we have. If we had a 2 rupee coin here, then there will be another branch and there will be 4 here, because from 4, if you spend 2 rupees, you can come to 6. So we can do this until we find this 0. Why does this 0 important? That is what we are going to discuss next. Now, let's formulate this. Let f of r be the minimum number of coins to form a sum of r. It means r, let's say r is, okay, if we need to pay r rupees, if r gives the minimum number of coins that we need to spend to give R rupees, and that is the answer for our problem. This R is going to differ from case to case, but this function f which maps this R to the minimum number of coins, and that is what we need. So when solving this, you can see that f0 is 0, because to pay 0 rupees, you do not need any coin. That is obvious. So to pay 1 rupee, you need 1 coin, 1 rupee coin. To pay 2 rupees, you need 2 coins. Why? You need 2 1 rupee coins. Now in Fibonacci case, you can see that here we had this structure. We have these initial conditions. These are the initial conditions. Initial values. These initial conditions, we have this initial condition, then we define this recursive function. So we need this initial conditions, and you can see that in this recursion tree, we stopped iterating when we find one of these initial conditions. Why is that? We know the exact solution for these initial conditions. So that is how a recursive structure is being formulated. In dynamic programming, we are pretty much interested about recursion structures, because that is what we are going to optimize using dynamic programming. In dynamic programming, all the properties that we have discussed earlier leads us to this notion of recursive structures. If you have a recursive structure, you can use dynamic programming to optimize that. So this recursion tree is utmost important in the context of dynamic programming. So there is another way of tackling these problems, and that is by finding the states. That is that will be discussed by Praveen in the latter. So for now, let's say that we are optimizing recursive structures using dynamic programming. So this is a recursive structure. You can see the recursion tree here. So then now you might see that why this f0 is important, because we exactly know that to pay 0 rupees, we need 0 coins, and this is the initial condition of the base case. I forgot that name, the condition of the base case. So f0 equals 0 is the base case for this problem. Okay. So if we know f0, then we can find any fr for any given r. So let's see how we can do that. To do this, we need to formulate this using mathematics. As we have formulated the Fibonacci sequences in mathematics, we need to find a recursive structure which gives the solution for this problem. Now, we know that f0 is 0. Forget about this part for now. I will get back to that after defining the recursive structure. So we need to find the minimum of fr minus 1, fr minus 3, and fr minus 4. Why is that? Now let's come to this structure. Now we have drawn this structure, that is okay, but how to find the optimal solution using this structure? Now let's say we need to find f6. If we need to find f6, we can find f6 using f5, f3, and f2. That is what this tree structure means. So if we can find the optimal solution for 5, and we can find the optimal solution for 3, and we can find the optimal solution for 2, f5, f3, and f2, if we can find the optimal solutions, then we should be able to find the optimal solution for 6. For f6, that is what we have discussed in the very first slides. Okay, so let's say that in this problem, the optimal solution for f3 is, we can see that it is 1. Because from 0, you can spend a 3 rupee coin and come to 3. So the optimal solutions, the minimum number of coins to form a sum of 3 is 1. So f3 is 1. I am considering this level right now. This level of this tree. Okay, f3 is 1. Then f5, you can find the minimum number of coins, and you can see that it comes from this part. And that is 1, 2. You can take a 4 rupee coin and 1 rupee coin. So f5 is 2. What is f2? F2 is, obviously you should take 2 1 rupee coins. It is also 2. Now, to find the optimal way of paying 6 rupees, you should take the minimum of this, because the goal is to have the minimum number of coins. So you should find the minimum. That is why I am finding the minimum here. If r minus 1 is, if 6 minus 1 is 5, if r minus 3 is 6 minus 3 is 3, if r minus 4, 6 minus 4 is 2. This comes because fr minus 1, if we are in the fr minus 1 state, then we can pay 1 rupee and come to fr. Same goes for these two values as well. Now, when we have these values, then after that, we need another 1 coin to go from either of these to 6. So that is why I have added 1 here. So I think this is clear. So what is this guy doing here? This is, I added this one just to make sure that I formulate the math accurately. That is because let's say that r is 1. When r is 1, we encounter something like, here we get f0, here we get f minus 1, and here we get f minus 2. If r is 1, this is f0, f minus 2, and f minus 3. Now we don't know what is f minus 2 and f minus 3. That does not make sense, right? Because we cannot pay minus 3 rupees. We cannot pay minus 2 rupees. So when we are finding the minimum, if we have this argument of this function a negative value, we need to make sure that it does not affect the answer. So to make sure that I do it correctly, I assign this to infinity. Now this infinity can be sometimes float infinity, but you need to make sure that every number, every fr that you are having in this context is less than the number you assign here. It can be float infinity, or if you can find an upper bound for this fr, you can use that upper bound for negative values. That is a way you can deal with this guy. So I wrote this part only to make sure that I formulate it correctly. Otherwise, this will have some pathetic cases. Yeah, this is not defined. Or this might end up in an infinite loop or something. It can lead to catastrophic events. So to make sure that those things does not happen, I formulated this as well. Now, when you are using dynamic programming, when you have found, let's say 3 here, let's say you have found this f3 here, then this branch goes away entirely. Here, if we have found 2, this branch goes away entirely. This branch, these are no more, and you should find 1. So this you need, these are not needed. So you can see that it is pretty easy now. You have reduced a lot of computations. So that is how we optimize a code using dynamic programming. So this is the end of the part that I am going to discuss. So I would like to hand the presentation over to Praveen to discuss some advanced topics and discuss some examples on dynamic programming. Over to you, Praveen.
Right. Thank you, Athulya. So, Athulya gave a great. Before that, am I audible?
Yes, you're audible.
Yeah, thank you. So, Athulya gave some excellent examples regarding dynamic programming, and with the goal of giving you an intuitive idea of what dynamic programming is. So, I will try to give some example problems so as to motivate how you should go about trying to find the optimal states as well as the state transitions. So I hope you guys can see the screen. Can anyone confirm whether they can see the screen?
Yes, we can see the screen.
Okay, thanks, Atul. Right. So, before we go on to problems, I would like to give a short introduction on the steps I roughly follow when I personally try to solve DP problems. However, this is not an exhaustive list. This is just some general pointers. Unfortunately or fortunately, with DP problems, the approach tends to differ from problem to problem, but I will try to give you an overview. So, step one is to understand the problem correctly. So this is not for DB problems. Like in many competitions, we have like solved the problem for like half an hour, and after half an hour, we realized we read the problem wrong and had to do everything all over again. So just make sure that it's just a general tip, right? The next one is we need to check whether the problem is a DP problem. So that is not particularly easy because, as Athulya said, sometimes we cannot exactly differentiate between greedy problems, DB problems, and there are questions that are designed to mislead you. So there might be a graph like problem, but the actual method that you need to use is DP. So this requires experience. So the best way to get that experience is to solve as many problems as you can. And also, whether you solve it or not, go back to the editorial. So for certain problems, you might be able to find solutions that others have done and try to read them. They might have done it in a better or a different way. Next, as Athulya mentioned, we need to find a recursive structure or subproblems. Because that's the idea of dynamic programming. We solve the problem by trying to solve simpler or smaller versions of the problem, and we combine the smaller solutions to form a solution, and we do this iteratively until we get the desired solution. Now the other step is to find the state of the subproblems. Now this is a bit so you might think that these two steps are the same, but it's not. So for example, the recursive structure is like the recursive formula in the Fibonacci problem. There you basically first start with the formula. The state actually is not that complicated in that problem. However, sometimes before you actually understand the recursive structure, you might be able to figure out the state. And after you figure out the state, you might be able to go for the recursive nature. So um, this is so usually we find the recursive structure and identify the states to define the recursive structure. But if you try to identify the state first, you might get a clue as to what the recursive structure might be. So these steps can like interchange. Now, most of the times, and I think even the problems I have lined up today are like this. The sub-problems have a similar nature to the original problem. However, there are problems where the sub-problems are completely different. For example, there are interesting cases where we have the target problem, which breaks apart into sub-problems, which is a completely different problem, but those break apart again to form a smaller version of the original problem. So it somewhat alternates. So there are very interesting forms that the DP problems can take. So you need to, like, once you find the recursive structure, you might need to do extra work to solve the sub-problems before you combine the recursive structure. And this is something I personally like to do. So especially if it's a math type DP problem, I sort of write the recursive structure in a function notation because I'm more of a maths guy than a coding guy. So is Atul actually. So I prefer that format, but some people just prefer to use just the DP version. So basically using arrays to define the DP problem, but that is somewhat relevant to your own preference. This is the step I hate. Defining initial conditions. So you might have noticed when Athulya was solving his problems, you need to define. So it has a recursive structure, but if you have ever tried to write a recursive function without a stopping condition, basically you might have gotten something like max stack size restore, something like that. So basically it will iterate without stopping. So you need, or it might, so the initial conditions are important, and I don't know, for me it can be difficult to find the initial conditions because especially because of the way you define the problem, the initial conditions where to start. So let's say, for example, the problem has like goes 1, 2, 3, 4. You need to find the first element, the second element, the third element. Quite often, rather than trying to find what the first element, artificially adding a 0th element might make the problem easier. So there are challenges with defining initial conditions, and in fact, in team competitions, I in fact get the other two's help with the initial conditions. I can usually do the other parts, but initial conditions I often get wrong. All right, so finally we code up the solution. So these are the steps that we use to solve the DP problems. Now let's try to apply them in several problems to get a feel for it. So none of the problems that are chosen are particularly hard. There are several that might be considered intermediate, but none of them are particularly hard. So I hope everyone will be able to follow. And even if you can't, it's okay, because like these things require a certain deal of practice to really understand. So when I started doing DP problems, I could never find the recursive structure or the states. But I don't know, after doing like several, like, I don't know, 20, 30 problems, things started to click. So like you might have a sort of a blanking period before you actually start getting the hang of it. So please keep at it. So let's consider this problem. There is something that I haven't mentioned here. I'll just say it in wording. So there's a sequence of L integers b1, b2 up to bl, and the problem, so it's not particularly clear here, but the problem actually gives integers of the form 1, 2, 3. So the input of the problem is actually two numbers. It just gives n and k. So there's a sequence of L integers which is actually 1. So actually it's there. Sorry. The way it has the problem has stated is might not be that clear, but if you look at this quite carefully, you will realize actually. Okay, so there's a bit of an error in this problem, so don't worry about it. But the way the problem actually gives is it only gives two numbers, n and k, and what you have is a sequence of numbers 1, 2, 3, etc. up to n, and you need to find what's called a good sequence, right? So a good sequence is if you consider a sequence. So let's say, so the input, just to clarify, I think I might have made it a bit misleading. We have n, they give n integers. So they don't actually give all the n integers, just the last one. So we need to like understand there are integers going from 1 to n. And they also give a number called k. And they are asking for the number of good sequences. And since the answer can be very large, we need to output it modulo this number. Usually this is because the number can be very large, but there are certain instances where this modular thing can be used as a exploit for solving the problems, but most of the time this is just to make sure that languages like C++ don't overflow, and Python can handle large numbers and other languages, but they get slower if the number gets too large. So anyway, we need to find sequences of length k which have this good property. So what is a good sequence? So a good sequence is k numbers, but let's say B5 must be divisible by B4. Okay. So right. So they are asking us for the number of good sequences. Now, like the most naive way, so it's always good to consider the most naive way. The most naive way would be to consider all the sequences of length k. So and a sequence is a subset of the original sequence. So let's say I will take a concrete example with, let's say, 10 numbers. So example of a sequence is something like this, right? So they don't need to be consecutive. So this is important part. So you need to understand what the question is asking. It's not something like a sub-array. If it was a sub-array, the numbers need to be consecutive. But since it's a sequence, the numbers don't need to be consecutive, but the ordering of the numbers should remain the same, right? Okay. So this is a sequence. So what a good sequence is if, let's say, this number is divisible by this number. So in this case, this is not actually a good sequence. Right? So an example of a good sequence would be something like 1, 3, 9. Because here 9 is divisible by 3 and 3 is divisible by 1. So the way I have written the question might be a bit misleading. I have actually skipped a few steps for sake of brevity, but this is the problem statement. Right. So as I mentioned, the naive way is to consider all the sequences of k-length and check for goodness. So this can be done like using using many methods. So I think you might be able to code a relatively simple function which goes through all the sequences of length k and then check for goodness. So something like that would so since we need to consider all the sequences of length k, we need to, so let's say there are n numbers, we need to choose k of them. So it will take like this number of iterations. So so n and k are quite large in this case. So actually, I think it's on the order of 10 to the power 5 or something. I don't remember exactly. Actually, that is also something that is important to consider, the size of the numbers. But I have forgotten to include it here. However, the naive way takes a long time because, as you know, this is n factorial or n minus k factorial. And if you are also checking for goodness, you might need to do another k iterations as well. There are ways to do that without doing it, but suffice to say, this takes a very long time. Especially as k gets quite close to n over 2, this can take quite a long time. So this is not particularly a good option. So let's erase everything. Right. Now, So now we need to consider the thing that Athulya mentioned. We need to consider the state. And also, like whenever you are trying to solve a DP problem, what you are trying to actually do is, so with the subset thing, we were considering all sequences. But you will realize, so let's say we started to consider sequence like this. So let's say K is 4. We need sequences of length K4. If we choose 5, there is no point in choosing 7. Right? So this is the naive, like the checking all sequences is the brute force approach. And in fact, one of the things that I always do when trying to solve DP problems is first think of the brute force approach. Because when you consider the brute force approach, you can find inefficiencies in the brute force approach. So here, one inefficiency is when we are considering a sequence, there is no point in considering number 7 when you have chosen 5 to be the previous number. Because clearly 7 is not divisible by 9. There is no point in selecting that. So now we are starting to see a state and transition pattern. So when we are selecting the, let's say, let's say Bj, so of the K long sequence, if we are selecting Bj, the selection is affected by what we chose for Bj minus 1. Right? So one natural thing to consider when considering the state is this transition. So let's try to solve the problem considering this. Now, and another obvious state is actually where we are at the moment. So we can consider numbers up to 7, numbers up to 8, numbers up to 9, and numbers up to 10. So when we are trying to solve for 10, we can use the solutions that we have created for previous numbers to find the solution for 10. So let's try to come up with the states. Right. Now, usually we denote the DP problem with just the DP. And since we have identified 2 states, I will write it like so. I will write it as X and Y. Right. So this is one thing that we need to consider. But another thing that we need to consider. So let's say we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So let's say we have already come up with, let's say this thing. I will also add some more things. Let's go up to 18. And K is equal to 3. So now when we are trying to choose this, if we have already chosen 1, 3, and 9, we cannot choose 18 because K is equal to 3. However, if we didn't choose 9, we can choose 18 because K is equal to 2. So another thing that is important when building these sequences is how many numbers that we have chosen so far. So that is why we have 2 states. One of the state is which number we are considering. This is important because we need to consider when we are considering whether to add a number or not to a sequence, we need to consider what the previous number was. So for any sequence, we need the last number in the sequence. So this is actually depicting the last number of the sequence. Right? The next one that we are considering is, let me just check the time. The next one we are considering is how many numbers have we selected? We selected in the chain so far, right? So let's try to build up the solution using these two states. So let's start with a very simple thing. There's actually an important distinction that is coming up later. So let's say we are at this state. So how would we try to um, uh, calculate this solution? So dpxy represents the number of ways to create a chain of length y. There is the number of ways to create a chain of length y with the last number being x. Okay, so let's go to the next slide. So we are trying to calculate dpxy. And if you actually are, if you want to know, the final solution is simply the sum of this. So basically we add up all the chains of length k that end at the ith number. So I equals 1 to n. We just add this up and this is the final solution, because we need length that we add up the chains that end in 1, end in 2, end in 3, and end in 4, etc. So a chain that ends in 1 is completely different from a chain that ends in 2. These can never be the same. So we are adding distinct solutions. So this will give us the final solution. Right. Now to calculate this, one way we could go about this is, so we are choosing x as the yth element. So obviously there is a case. If y is already k, we don't need to, okay. So if y is k, so if we are, let's say, actually, no. I will first not consider the edge cases and just write the general case, okay? So obviously, if we are adding x as the yth element, then the previous chains we need to consider must be, right, must be, if you suddenly stop seeing the screen or something, please mention it. So must be of length. Something is happening with my drawing pen. Okay, please excuse me a moment. There's a few issues we need to work out. Okay. I'm sorry, because there was a issue with the my drawing tablet. Right. So if we are choosing the x number as the yth element, clearly the previous thing we need to consider must have y minus 1 elements, right? So as an example, if we are deciding to choose 9 as the third element, so the previous part of the chain must have a length of 2, like so. Then the way we do that, so if we are choosing the xth element, all the elements that we consider before must be divisible by that. So one way to do that is to iterate over all, let's say, m, where m is divisible, m divides x. Okay. So a concrete example would be, if you are choosing 9 as the third element, we go through all the numbers that divides 9. So it is 3 and 1. So we consider, let's say we are trying to choose 9 as the third element. So the way to choose 9 as the third element in a chain is we sum up 3 of length 2 and 1 of length 2. Because you cannot choose 6, 7, 8, 5 or anything else. It has to be this. Because as the problem states, to be a good sequence, this number must be divisible by the previous number, right? But there is, and of course there are special cases. So for example, if y is equal to 1, if y is equal to 1, then we need a chain of length 0. So those are things that you need to consider when doing the initializing step. So I won't go into those because I think you guys can figure this out. But what I want to emphasize is the thinking patterns, right? So this is a okay method, but the way we are doing this is not efficient. And this is actually why I chose this problem, because the way you sort of go about solving the problem can even, so the two people might consider the same state transition. So the state space, the way the state space is defined. So we consider the last number and the length of the chain as the state, and we use previous states to calculate that. Two people might come to this same conclusion, but the way they are using the recursive states, how they are combining the states, can create a huge difference in performance. So, like an easy way to do this, so we need to sum up all m which 9 divides, which divides 9. So 3 and 1. So one might actually implement this by doing a naive iteration. So we start at 9 and consider all the previous numbers. And if it is divisible, we add it to this. So basically it would be like for, I will write in like Python for I in range, let's say 9. So let's say actually for m in range, if m is divisible by, let's say x, m is divisible by x, we add this here, plus equals this. Otherwise, we don't do anything. However, this has pretty rubbish complexity, because for each x, you need to iterate back. So roughly, you need like x number of operations for each x. So it will be sum of x going from 1 to n, and it will also be multiplied by k, the maximum value of. So it will be something like this, which will have quadratic performance. Now you might be able to optimize this by trying to cleverly find all the devices of given numbers beforehand, but that also takes a lot of time to implement, which eats into the valuable time that you have, that you could solve other problems. So this is something that most DP problem solvers face. So because they, I don't know how many of you know this, but there are sort of two ways that you can combine subproblems to solve the problem. So to do DP, that is called push and pull. So this is actually a pull method. So the reason that, so this is pull method. In a pull method, we calculate xy. When we want to calculate xy, we pull the required information from the previous states. So these are the previous states. So here we are, that is what we are doing. When we are calculating dpxy, we pull information from lower states that are smaller than this. And if a person only practices solving DP problems using the pull method, they might have a slightly more difficult time with this problem because although it is possible, it is somewhat more difficult to efficiently find numbers that divides X in an efficient manner. However, there is also another method, and that is called push method. Here, instead of DPXY pulling information from previous states, so this is actually pull method. Oops. In the push method, previous states, as we calculate previous state, we push the information into future states. So in this case, what we do is instead of calculating dpxy using the summation, so this is not what we do. Instead, when we calculate dpmy, so let's say we are calculating this one, we push the information from this onto other states that might use this. So for example, let's say we are calculating dp32. This is, as I mentioned, the number of chains which end in 3, which have 2 elements. So things like 1, 3, we cannot, that's actually the only possible one because there are no 2, 3 is not a good chain. So actually this will be able to work. So once we calculate this, we can push the information to other states because so let's say we have dp3. We know that the values that can follow 3 are multiples of that. So basically we can go through another loop. We can go through another loop that we basically push the information. So 2 plus 1 equals dp3 1. So here we are sending the information of the number of chains with 3 ending in 3 with length 2 onto other possible values which are multiples of 3. So instead of this part pulling information from this, once we have calculated this, we push the result into future operations. So this is the push method. So one might, why is this more convenient than the other one? It's because of this. The number of iterations will be lower because let's say we are calculating dpxy. And now we are pushing the information into future states. So how many iterations do you expect? The largest number is n, and we multiply. So we don't multiply by 1, but the next future state is x times 2, x times 3, x times 4, etc. And we go that up to a number that is either n or close to it. So the number of expected operations is n divided by x, roughly. So the integer closest to this, right? And times y, because we have y length chains. And we need to sum that from x equals 1 to n. So this actually, the number of operations becomes something like this. So actually we can take y as well. And I don't know whether you know this, the sum of reciprocals can be approximated by log n. So the number of operations here is yn log n. So this is the difference between the pull method and the push method. So I don't want you to get the idea that the push method is always better than the pull method. It can differ. The thing is, you need to do complexity analysis to find which one suits the particular situation. Oops. So, right. Sorry about that. So, can people is the difference between push method and pull method, and why one is more advantageous compared to the other clear? Can the people who have understood it raise your hand? Okay, so there are a few people. I hope others have understood that it as well. If there's anyone who has questions, you can ask before, because that is all there is for this question. And if there are no questions, I will move on to the next questions. For the next questions, actually, I won't be discussing this in great detail, because the thing that I want to emphasize on those questions is the state space representation, actually. So if there's any question, please, you can unmute and ask, or leave it in the chat. But if there are no questions, we will move on to the next one. Right. Seems like there are no questions, so I will move on to the next problem. Right. So here we have a question. A shop sells N types of juices, and the ith juice costs Ci. Each juice contains some number of vitamins from a possible K number of vitamins. Jake wants to obtain all the K vitamins by expending the least amount of money. Find the minimum cost that Jake needs to obtain in order to do so. Print -1 if it is not possible. So again, this is not a particularly hard question, but there is an important thing that I want to mention regarding this question, which might be helpful for you in other competitive programming questions. And that is how you sort of encode the state when writing DP problems. So to sort of explain the question, we have different types of juices. Let's say it's A, B, C, D, E, etc. And each has certain number of vitamins. And the number of vitamins is not that large. And this is important. Okay. And you will see why this is important. Right. So the N is, I believe, N is less than or equal to 10 to the power 6. So that should have been there. I have forgotten to include it. So anyway, we have things like this, and let's say the vitamins are 1, 2, 3, etc. Drink A might have vitamins 1, 2, and 3. B might have 3 and 5. C might have just 5. D might have 6 and 8, and etc. It goes like this. And each drink also has some cost. This might be 100, this might be 50, so on and so forth. So this is not a particularly hard problem. There are 2 points that I want to emphasize. So before that, I'll just tell you what the two states are, because what we want at the end of the day is need to obtain all the K vitamins, and we need to do that by spending the least amount of money. So obviously, what we are trying to do is we are trying to find a subset of juices that cost as small as possible, but also have all the vitamins. So in a situation like this, as before, it is usually simple. We anyway need to iterate. So one state might be how many juices we have considered so far. So let's say that is X, the number of juices we have considered so far. But unlike this doesn't mean we are choosing the X juice. It just means we have considered all the juices up to, let's say, D or E. Right. What should the next state be? So in this case, it is not enough to consider the number of vitamins that we have collected so far. So because let's say we choose A and B, we will have 1, 2, 3, and 5. So we will have 5 vitamins. If we choose A and D, 1, 2, 3, so we will have 4 vitamins. Instead of, let's say, this 4 and 5, we will have 5 vitamins if we choose both of these. If we choose both of these, we will also have 5 vitamins. But there is no way to distinguish between those if we only consider the number of vitamins that we have collected so far. We need some way to encode what is the combination of vitamins that we have considered at this point. So what Y needs to be is a set which has the number of vitamins that we have considered up to we can consume up to this point. So let's say we 1, 2, 3, 5, something like that. So the DP state will be something like DPXY, where X is the number of juices considered up to this point, and Y is the subset of vitamins that we can get. Right? So how do we solve this? So again, I won't spend too much time on this. Let's say we have solved all the states up to this point. When we are considering this, we can consider 2 cases. Either we choose D or we don't choose D. Right? So regardless, so let's say this is the first, second, third, fourth. So DP3 and all possible things are calculated, and we are trying to calculate DP4, which is whether or not we include D is up to us, but we have considered D at this point. So we will have 2 options, either choose D or not choose D. Right? If we are choosing D, we can consider all the subsets that we get, all the subsets of vitamins that we get up to DP3, and then we can just add these vitamins into that set. So if there are duplicates, we don't do anything. If there are new vitamins, we can add that, and then we can also add the cost of D, or we can just not add D at all. So the DP state will be something like DPXY will be equal to something like, so actually the min. So this will be the cost with all the vitamins up to X, all the juices up to X juice considered with the Y subset of vitamins, the minimum cost. So this will be min DPX minus 1 Y, right? And also, actually, it's a push method is actually much easier here. So we need to push the DPX minus 1 Y union with the vitamins that are in D. Right? So basically, if Y is the set of, if Y is something like 1, 3, which is basically vitamin 1 and vitamin 3, Y union D will be 1, 3, 6, 8, 5. So if we take D, we will also have these vitamins in addition to this. So this is what we have. So basically, actually, we have DPX minus 1 Y, and if we choose to take D, we will have Y union D. So instead of this, we take the minimum of this and the value that we have already calculated for this. Right? So basically, we are pushing the information from this state onto this state. But when we are doing so, we need to take the minimum of the value that we are pushing and the value that might already exist in this state, because we might have reached this state by a different path. So there might already be a cost associated with it, and we only update it if this new thing that we have found is less than that. Okay. And also there is the option where we just don't choose D. So we also have dpx y is equal to dpx minus 1 y, and also we need to take the minimum of this and this. So this is basically the situation where we don't choose D. So I only gave a brief overview. So those who are familiar with DP might already have solved this. Those who are new to DP might have a difficulty following this a little bit. So don't worry, just go through the problem again and try to use the things that I have mentioned to solve it. So it's not a big deal. However, the thing that I want to say is, as you might have seen, for DP states, earlier it was numbers, but now we also have sets. And this is another technique that you need to polish when learning to solve DP problems. One is recognizing states. The other is considering state transitions, how to combine subproblems to solve the problem. The other is like what sort of techniques to use, the push method or the pull method, or there might be even different variants of it in other instances. So how to actually implement that is also important. As you can see, it's not just a matter of style. The way you do that can also affect the complexity of the algorithm, either time wise or the number of lines you have to write. The other skill is how to efficiently encode the information in a state. So if you are using something like Python, you might consider using something like a set. There's a set data structure, but this will work. But taking set unions and things is very cumbersome. Not cumbersome. It's quite computationally complex, and because these are slightly heavier data structures, so it can slow your program down. So one technique I would like to show is you can use numbers to represent set, and this is why this number of k being small is important. So in DB problems, the way you usually represent set is using a bit set. So basically, we take a binary number like this, and what this binary number represent is a set. So how does it represent a set? If the bit is set, so if it is 1, that means we are choosing the corresponding vitamin. If it is 0, it means we are not choosing the corresponding vitamin. So this number will actually represents this set. We choose the first vitamin, not the second vitamin, the third vitamin, not the fourth vitamin, fifth vitamin, and the sixth vitamin. So you can also choose this to be the first vitamin. That might be more convenient in the programmatic sense, but it's up to you. So you can use these numbers to represent set. The advantage is it's very easy to take things like unions. So basically, if you want to take a union, we just owe the the two numbers. If you owe the two numbers, you take a union, because the way O works. So if both sets have the same element, we just have the element. If at least one of the sets have element, we also have the element. The only way we don't have the element is neither of the sets have the element. So we can just use the OR operation to do set union. You can use the AND operation to do set intersections, and so on. So that is the other message that I want to say. The main message is you need to do problems to understand different ways to encode state in a DP problem. So I have given one specific example where you can use just numbers, bits, to represent a set. This is called a bit set. So that is a technique. So now when you are implementing it, you don't need to bother with extremely complicated data structure. You can just work with numbers, binary numbers. And so even in C, you can code this solution up, which doesn't have any data structures built in. Right. So I was thinking of discussing this problem as well. But I think given the time considerations, I probably skip it. I might send this to you. So the reason that I wanted to discuss this is this has, depending on, oh, actually, there's one thing I want to mention. So with the previous problem, so I mentioned we have two states, dpx and dpy. But in fact, this state is not really necessary, because whenever you are considering this, when you are trying to solve the problem up to D, the only thing you need is up to C. Problems, the number of ways with B and A are not really relevant. It was not in the case in this case, because we need the number of ways to construct chains with ending in different numbers to calculate 9. But for this one, you only need the previous state. So whenever you have something like this, it is somewhat beneficial to just drop this state and just keep a track of the previous state when you're considering the current state. So here we actually only have dp previous with all possible sets and dp current. And we use the previous state to calculate the current state. And in the next, when you consider the next juice, the current state becomes the previous state. And in fact, when like in very competitive programming problems, sometimes even constructing arrays can give a time limit exceeded thing. So we actually use two arrays, so two buffers, which we swap. So we use this as the current. So we use this as the previous array and use that to calculate the current array. Then we swap the pointers, or like in Python, you can just swap the references, and then use this and use the previous buffer as the current buffer and use this to fill it up. So this is basically a way to do this problem without doing additional memory allocations. So if there were like 1,000 juices with 1,024 10 vitamins, we will have like a memory complexity of like this. But if we use this system, you only have to store 2 times 1024 if k is 10, or 2 times 2 to the power k things in memory. So there are things like that you need to consider as well. So as I was going to mention, I was going to solve this. I think you need about 3 states if I remember correctly. So a problem with more states, but I think with the time I won't have time to solve this. So instead, I will just end by considering this one, which is an example where the states are slightly weird. So we are asked to calculate the number of ways for tiling a m by n grid with 2 by 1 and 1 by 2 tiles. So I think you might be starting to get bored because this has been a long session. So I will end this quickly. So basically we are given m by n grid and we are asked to tile it using 2 by 1 and 1 by 2 tiles. So this is a 2 by 1 tile and this is a 1 by 2 tile. And they're asking the number of ways to do that. Now this is interesting because this is a very geometric problem. There are no clear numbers where we can use the usual structure. So how can we do dp something as a combination of other things? So it's not particularly clear. But let's just say we can do this, and let's say we are trying to solve this. So a natural way one might go about it is to consider row by row. We fill this row, and then we fill this row. Now, one might be, okay, actually that's not possible because there are blocks that span 2 rows as well. So yes, that is a problem, but let's try to see what we can get if we try to solve it like that. So let's say we are trying to fill this problem, fill this row. And we have already filled this row. So if we decide to put something like this here, you will see that we have no option here. We have to accommodate the decision that we made earlier. However, if we decide to put something like this here, we are quite free to put anything we like here. We can either put a block like that or a block like that. We have both options available. However, if we already fill this, we cannot put a block like that. So I think you are starting to see a bit of a pattern here, right? So the way we do this is actually quite clever. We need, so I won't go into details. You need to think about this, but the states for this problem are actually can be represented in this format. So these sort of represent a part of a tile that each cell can have, right? So if we are trying to fill this, we need to consider what the tile above has. If the tile that is directly above has this thing as the decision, we don't have any degree of freedom here. We need to put this, right? But if it is something like this or this, we are not constrained. We can put this, this, or this. But we cannot actually, at no point we put this, because after we have finished this row, all the things are done. We only put this if the above row has this in it, right? The other thing is when we are filling a certain square, we need to consider what is on top. So we need the previous state, as well as the thing that is in that cell. In addition to that, when we are filling the current cell, we need the cell immediately before, because if it is something like this cell has to be like this. So this is the structure that we actually exploit. In fact, there is a way to simplify this structure even further, but I won't go into details because again, it will go on for a long time. But I am not going to write down the recursive nature of this problem. So how to calculate so basically what dp nth row this thing is. So the dp state is actually the row as well as the symbols that is in the row. So basically something like this. And then you can use this to calculate row plus 1. And as we are filling this, we need to consider the state previous as well as the state above. So those are the states. And as I mentioned before, we need to encode these symbols mathematically. You can use letters and strings as well, but as much as possible, try to use numbers. So you can encode these using binary or something like that. So that is the thing. So the reason I included this was to show you that the states can be very different things from numbers. So just because it's a geometric problem doesn't mean it's not something you can use DP in. So that is all I have for today. So if you guys have any questions, you can ask. I hope you guys understood everything. And
So Praveen, then we can do the Kahoot, right?
yes.
Okay. So unfortunately, we can only accommodate 10 participants. So we can use this game pin. So we will do this on a first come first serve basis. We don't have other options. You can see this, right? Let's make it quite quick, otherwise you will lose your spot. Okay, we have our first participant here. Okay, we have 8 spots left. We have 3, 4. We have 6, 7, 8, 2.
Also, in the meantime, if you guys have any questions regarding the session or anything outside the session in DP or um, competitive programming, feel free to ask or put a question in the chat.
Yeah. We have 9 participants. We're going to accommodate one more. Okay, we will give you 30 seconds. If we will start. If someone is trying to join, please raise your hand. Otherwise, we can start. Okay, we have it. Now we can start. Okay, we are going to start the session. So I know that I hope that you know how to play a Kahoot. Okay, so the first question is, what are the 2 main properties required for a problem to be solved using dynamic programming? Please select the corresponding shape in your screen. You can see the shape here. Same shape will be visible in. Select the shape which corresponds to the correct answer. Okay, so the question is, what are the 2 main properties required for a problem to be solved using dynamic programming? Recursion and loops is not what we have discussed. We have discussed this in the first part of the discussion, and we agreed that optimal substructure and overlapping subproblems are the 2 main properties of a dynamic programming problem. Praveen, anything to add?
Right. Yes. Also, even if you got this wrong, you might still be a DP expert because people who solve DP might not be actually thinking about these things like in like words. They might have the idea. So like since recursion and loops are used quite often in DP, that they might have choose the answer as that, but like the official answer is the optimal substructure and overlapping problems. But recursion is quite often there, but most of the time you need to understand is even though mathematically we have recursion, most of the time when solving it we don't use recursion because it tends to be quite a bit more expensive in expecting certain cases. So if it's simpler to write, you can go for recursion, but most of the time with overlapping subproblems especially, you tend to have repeated calculations. So that's it. You can go to this.
Okay, so let's move on to the next question. And here we can see this scoreboard. Mr. Sri is leading right now. And we have CodeX and Shell in second and third places respectively. Then we have a true or false question. The question is DP is always faster than greedy algorithm. So we have 8 seconds left. Okay, we have divided answers. So I think the confusion is about the speed, right? This is
Yeah.
not the speed. Sometimes the greedy algorithms cannot solve the problem. It might be faster, but it sometimes
Actually, more often than not, greedy
often
algorithms are faster.
faster. So that is a tricky question. It doesn't matter if you have got it wrong.
If you write a greedy algorithm, it will be quite a bit faster, but it will be wrong. It can be wrong. So
And
actually, if you have a problem which can be solved using DP as well as greedy, go for the greedy algorithm, because most of the do the complexity calculation, but most of the time greedy algorithms will be quite a bit faster. And in fact, when you are solving the DP problem, if you realize you don't actually need the previous states, that means it's a greedy problem. So you can use the greedy algorithms.
yeah, exactly. So I think that gives a nice explanation. Okay, Mr. Shri is still leading the scoreboard, and we have Yasiru and Hai in the second and the third places. Next, a quiz question. In the Fibonacci sequence, why is the naive recursive solution inefficient? Okay, we have 5 people who are saying it uses too much memory. Actually, the naive recursive solution uses less memory, because when we use dynamic programming, we need to store the solutions that we have already obtained. So it takes a lot of memory when compared to the recursion. The problem with the naive recursive solution is it repeats the same subproblem many times because of the overlapping substructure property in a dynamic programming problem. Praveen?
Yes, I would like to also add 2 things. So there are versions of DP where basically we only use like the previous 2, as I mentioned, like all the states might not be necessary. So if you only use the previous 2, actually the non-recursive implementation actually will use less memory than the recursive implementation, because the recursive implementation, although has to create a stack frames for each of the recursive function calls. And also there are certain ways where you can use matrix algebra and mathematics to solve it extremely fast, and that also uses quite a bit less memory than the naive recursive solution. But the most suitable answer here is it repeats the same subproblems many times, because the main problem with the naive solution for the Fibonacci sequence is not the memory limitation, but the fact that it is slow. That limitation comes before the other limitations.
Okay, so the next question. Before that, the scorecard. Okay, Mr. Shi is in the third place now. Yasiru has climbed up to the first place, and we have Hai in the second place. Next, we have a true or false question. Storing subproblem results in DP helps save time but use extra memory. Okay, Praveen, any comments?
Right, I may have given the answer
The
in
answer
the previous explanation, but yeah. So again, since we are storing subproblems, it saves time in a way, I would say, but again, use extra memory. Because we store subproblems, we don't need to keep evaluating the subproblems again and again. But as I mentioned, when you are solving DB problems, you need to try to make the set of subproblems that you use for a given instance as less as possible. So we saw several instances where we can basically ignore a lot of the states, just consider the previous state to solve it. So because otherwise you might run into memory limitations. That is also something you need to consider.
Yeah. Okay, so we have 10 more questions. We'll make it faster. Okay,
I
here's
probably
the...
should skip the make summarized explanations.
Okay, okay. Yeah, that is what we should do. Next, we have the next question. Which of the following describes optimal substructure? Okay, the majority have got the answer correct. So the overlapping substructure is solution can be built from solutions to smaller sub. Since we have the overlap, we can use the solutions that we have already mentioned when we are finding solution for a certain subproblem. Do you have anything to add?
Yep, I think it's clear.
Okay. Okay, we can move on to the sixth question now. We have a total of 14 questions. In DP, overlapping subproblems means that the same subproblem is solved many times in naive recursion. Okay.
So I think it was explained nicely in Athulya's lecture. Maybe the wording confused the audience, maybe.
Yeah, I think the wording confused. In DP, overlapping subproblems means the same subproblem is solved many times in naive recursion. Overlapping subproblem, the meaning of overlapping subproblem is when we are using naive recursion, we are solving the same subproblem again and again. That is why we are optimizing. That is what we are optimizing using dynamic program. That is what this wording means. If you have read it carefully, you might have get it correct. So the way is scoring more in Kahoot is to not be in panic. That is advice that I can give. Okay, so in DP, what is the trade-off when storing results of subproblem? Trade-off of storing results of subproblem. I think we have given the explanation for this problem as well for a previous question. Okay, let's time move. Yeah, we can see that 7 people have got the answer correct. So it means that you have got it correct. You have understood that, and the other 2 people might have confused, or they are confused with the word, because all the solutions looks the same. We have the scoreboard has not changed. The next one is a true or false question. Every problem that can be solved with recursion can also be solved using DP. Okay, we have 7 people have given the correct answer, and this theory has been explained in under the properties of dynamic programming. We discussed that we need to have a substructure nature, the optimal substructure, the optimal substructure within the given problem. Otherwise, we cannot use dynamic programming. Okay, the next question. Which of these problems is not usually solved with DP? Solved with DP. Okay, so 6 people have got the answer correct, and there are 2 people who gave the answer the longest common subsequence. Actually, when we were designing this problem, we knew that you have covered searching and sorting algorithms in the last session. So we got that also into consideration. So longest common subsequence can be solved using dynamic programming. You can see how you can solve that using dynamic programming leisurely after the session. So the correct answer is merge sort.
Yeah, merge
Anything
sort,
to
it's divide and conquer.
divide and conquer. So you
They
know,
are actually
pretty much same, right?
pretty same actually.
Pretty
So
same.
the confusion is understandable.
Yeah.
One might say it's the same, but the thing is we usually label it as divide and conquer.
Divide and conquer. So there we don't have that overlap in nature, right? Because the subproblems are independent, sort of independent in divide and conquer. Okay. True or false problem. All optimization problems can be solved with DP. Okay, false. All optimization problems can be solved with DP. We have discussed this. We have explicitly mentioned that we cannot solve all optimization problems using dynamic programming. We need to have those 2 properties that we have discussed, the optimal substructure and the overlapping substructure properties. I think it's clear. Anything to add, Praveen?
Yes. So the other thing might be like the states need to be like countable. So if you are trying to do something on the real numbers, it is difficult to use DP. Like the minimum of a function on real numbers, you usually use things like gradient descent or other methods. So yeah.
Gradient descent, Newton's method, or anything you can use. Yeah. So the set that you're considering should be countable. We hope that you know what a countable set is. Otherwise, you can go and search in literature, and it's widely available. Okay, the next question is, which statement about DP is correct? Okay, I think almost all the participants have got it correctly. DP only works if subproblems are independent. That is divide and conquer. DP reuses solutions of overlapping subproblems, and that is the correct answer. Anything to add, Praveen?
No, it's quite clear.
Okay.
No, it's quite clear.
Okay, thank you. So the next question. This is a true or false question. In DP, overlapping subproblems mean subproblems are independent. Yeah. We have the correct answer here. It's false. If the subproblems are independent, we usually don't use DP. We use techniques like divide and conquer. Praveen?
Yep. Yeah, I think the answer is in the question.
Yeah. In the previous question, we had the answer for this question as well. Okay, Yasiru has the highest answer streak of 12. Yasiru is doing great here. Okay. True or false question, guys. Greedy algorithms and DP always produce the same solution. Okay, that was very rapid. And yeah, we have discussed that in previous questions. and in the
Yeah.
discussion.
And
Yeah. So now we have come to the last two questions. See a quiz question, and this is a double pointer question. In Fibonacci, using naive recursion, how many times is Fibonacci 2 is computed in Fibonacci 6? When you're trying to find the 6th Fibonacci number, how many times you need to calculate the second Fibonacci number when you're using naive recursion? You have 1 minute for this question, so now try to get it correct, because if you get it correct, you will get double points. Okay. This we cannot actually explain. You should draw the regression tree. Then you will see when we are trying to compute Fib6, the 6th Fibonacci number, the second Fibonacci number would be calculated for 3 times. Okay. Probably anything to it?
curiously, I think you can use DP to solve this problem as well.
Yeah. Yeah. To find the number of times that Fibonacci 2 is calculated. Yes.
Use calculated when calculating Fib6, because you can count how many ways to how many times Fib2 is used by Fib5 and Fib4 and just add those to get Fib6.
Yeah.
So you don't actually need to draw the entire recursion tree either.
Yeah. I mean,
For
in
this
this.
simple problem, recursion tree is easy, but if this was a competitive programming problem asking for Fib n in Fib n or something like that, you can use DP to solve this, I think.
It is an interesting question, right? I think I have not encountered that problem.
Yep.
Okay, and then we have the final question. No, that is the final question. So Yasiru is the first. I think he has a very high streak. Yasiru is third. Sorry. Mads is second, and Laka is the first with 10,643 points out of 15,000 points. Yeah, so that marks the end of the Kahoot, and like to congratulate all winners and all the other participants. They have done a very good job. Yeah, so I think that marks the end of our session. If you have any questions, you can still ask. We will remain the session until you leave. So thank you guys for participating in today's event. I think we think that you have got something. You have learned something. So good night.
Good night, guys.
Uh, Thank you very much, team Insomniacs. We're truly grateful to have you with us today because that was a great session. Even I was listening throughout the time. The clarity and depth you shared have given our participants not only a better understanding of dynamic programming, but also the confidence to apply these techniques in real problem-solving scenarios. Your journey as a team rising to become Sri Lanka's #1 ranked team at IEEEXtreme and achieving impressive global rankings is nothing short of inspiring. The strategies and thought processes you walked us through today will undoubtedly guide many of us as we continue to sharpen our skills. On behalf of IEEE CodeX Sri Lanka team, we'd like to present you with this token of appreciation. This is, I'm audible, right? Nice. Sorry for the minor inconvenience caused. Let's get back to it. Once again, on behalf of IEEE CodeX Sri Lanka team, we'd like to present you with this token of appreciation. Thank you for being a valuable part of our journey and for investing your time and expertise developing the next generation of programs. Thank you very much. Hold on. So what's next? Looking ahead, we've got more exciting sessions lined up. These sessions will build directly on what we've learned so far and include hands-on experience to sharpen your problem-solving abilities. So be sure to mark your calendars and register now in our official website. If you haven't registered yet for IEEE Codex Sri Lanka session series, worry not. So head over to our official website where you can learn more about the competition, track your progress, and get to know sessions updates. The website QR is displayed for you all to scan it so that you all can register, go to the website. So scan the QR code now shown on the screen and register yourself to get full access in the IEEE Codex Sri Lanka official website. You can join our WhatsApp and Discord groups where you can receive important updates and stay in touch with other participants. Our QR codes are now on the screen, so feel free to scan and join. You can take a screenshot so it would be easier as well. And with that, we conclude today's session. Thank you for joining us and actively being part of this. Each session takes one step closer to becoming the confident problem solver you want to be. We hope you found today's discussion about both practical and inspiring. We'll see you again very soon in the upcoming sessions as we continue to unlock new techniques together. Until then, stay curious, stay consistent, and keep challenging yourselves. Have a good night. Thank you, everybody, who joined. And especially thank you, team of Insomniacs, for that valuable session.